So good morning or good evening, or better, good World Quantum Day. So, and especially welcome to this first IUPAP UNESCO International Colloquium on Physics for Society. So my name is Christine Darve, and I work at the European Spallation Source, the ESS, in Lund, in Sweden, and I will introduce this special event. So it's a great honor for us to have Professor Anne L'Huillier as a speaker for this first colloquium. So Professor Anne L'Huillier is a distinguished French-Swedish physicist. She started her career at Commissariat à l'Énergie Atomique, so in Saclay in France, as a PhD student until 1986, then as a permanent researcher until 1995, before becoming a full professor at the University of Lund in 1997. In 2011, Professor Anne L'Huillier won the L'Oréal UNESCO for Women in Science International Award for developing the world's fastest camera to record even at the attosecond, meaning a billion of a second, allowing humans to capture electronics motion inside the atom for the first time in science history. Therefore, enabling us to control chemistry through learning how to control those electrons. So she was awarded the Nobel Prize in Physics in 2023 with Pierre Augustini and Ferenc Klaus for experimental method that generate attosecond pulse of light for the study of electron dynamics in matter. So she became the 5th woman to obtain the Nobel Prize in Physics. So a dedicated scientist and mentor, especially for women in science, so she continued to shape the future of atomic and optical physics. So in our panelists also, we have Professor Silvina Ponce Dawson, who is an Argentine physicist and a leader in international science policy. So as president of the IUPAP, the International Union of Pure and Applied Physics, so from 25 to 2028, before that she was president designated and has been playing a key role in promoting global collaboration in science. So she's a professor at the University of Buenos Aires, and her research focuses on biophysics and nonlinear dynamics, particularly in cell signaling. And last but not least, so Dr. Amal Kasry, so who is the chief of section for the basic science in research, innovation and engineering at UNESCO. So she's leading programs that support research, education and innovation in basic and engineering science. So she designed and oversees initiatives to strengthen scientific capacity and to provide expert advice to member states. So now for the logistic part for this event, so following Professor L'Huillier's talk, so we will continue with a reflection and dialogue session, so which will be followed by an open question and answer session with the audience. So we warmly encourage you to actively participate. So feel free to submit your question in the Q&A box that you have on your screen, or raise your hand. So we will make this hour a vibrant and engaging celebration of Quantum Day. So Dr. Amal Kasry, so your screen is yours.
Thank you so much, Christine. Thank you all for such thoughtful and inspiring contribution to today's session. This launch of this curricula with the International Union for Pure and Applied Physics has reaffirmed the importance of connecting physics with the broader needs of society. Something that lies at the heart of UNESCO's mission. As we move forward with the International Decade of Sciences for Sustainable Development, I hope that this curricula will continue to foster dialogue, inspire action, and also strengthen the role of science as a common good. We really look forward to seeing the outcomes of this continued exchange and to working together to build more inclusive science and also informed societies. And to launch this curricula and also on the as we celebrate the International Year of Quantum Science and Technology, we are very happy that the first webinar or the first session of this series is about quantum sciences, and we are really, really honored to have Professor Anne L'Huillier to give us the talk or the lecture and the insights on the field of quantum sciences as part of the celebration of the year, and also to launch this series of webinars. Thank you very much, and I look forward to more of these engagements. Thank you.
Thank you, Amal. The International Union of Pure and Applied Physics is very proud to start this initiative in partnership with UNESCO to nurture a dialogue between the scientific community and the public in general. We are thrilled to have it started with a talk by one of the few women who were awarded the Nobel Prize in Physics, Professor Anne L'Huillier, to whom we are deeply grateful. IUPAP is the only international union that covers all areas of physics. Created in 1922, it now has about 60 territorial members. With this initiative, which will continue with 3 more colloquia in 2025, celebrating the International Year of Quantum, we expect to advance with IUPAP's mission to assist in the worldwide development of physics and to help in the application of physics towards solving problems of concern to humanity. We invite you to visit IUPAP's website to learn about the future colloquia in this series. And with this, I leave the floor to our invited speaker, Professor Anne L'Huillier. Thank you, Anne.
Thank you very much. So I will start by sharing my screen. Okay, can you see it?
Yes.
Yes. Okay, so this talk is really an introduction to the International Year of Quantum Science and Technology, very much inspired from the talk I gave at the opening day of for this International Year of Quantum at the UNESCO in February. So the title of this talk is Watching the Quantum World, and in particular with ultra-short light pulses. And this is the outline of the talk. First, I will go back in time. How did quantum mechanics start? Then I will ask the question, can we observe the quantum world? And towards the end, I will talk to you about watching electrons with attosecond light pulses. So the quantum started really 1900, I would like to say, with Max Planck that found Planck's law describing the energy of the electromagnetic light. This is he was trying to understand the behavior of black body radiation, which is the radiation emitted by a body at a certain temperature, so at thermal equilibrium. And he was trying to go from Wien approximation, which is in blue, which worked at low frequency, and the Rayleigh-Jeans approximation at high frequency. This is the red line. And he came up with the law that you see here, which is called Planck's law. And it's described by this green curve, which perfectly goes from the Wien approximation to the Rayleigh-Jeans approximation. But to write this law, he had to introduce the concept of light quantum. And you have here this quantum of energy, h nu, related to the frequency of the light. And at the time, he thought that this was a mathematical trick in order to find a good law, but it was really the beginning of quantum physics. Max Planck got a Nobel Prize for this discovery. And in this talk, I will actually put a small Nobel medal for everyone that got the Nobel Prizes in this field. And you will see that many have been recognized by the Nobel Foundation. Einstein, 1905, used this concept of light quantum introduced by Max Planck to explain the photoelectric effect. And here I'm representing this photoelectric effect not for a metal, but for a single atom. So here you have light being absorbed by an atom, and this leads to emission of an electron. The kinetic energy of this electron is equal to this light quantum h nu, where nu is the frequency of the light, minus a quantity which depends on the system, the atom, which is the ionization energy. And this was confirmed experimentally by Millikan in 1914. In 1905, this was this fantastic year of Einstein. He also discovered special relativity, and Brognier mentioned, but I will not talk about that since I'm concentrating on quantum. Niels Bohr, 1913, come up with a very nice atom model. He was trying to explain the spectra from atoms, and the spectra from atoms was made of lines. And it was very difficult to understand the reason for these lines. And actually, Janne Rydberg, who was from Lund, invented an empirical formula to describe this line spectra from hydrogen atoms. And you see this formula here, the Rydberg formula. So Bohr, using this formula and also the knowledge from Planck or Einstein, presented this model that you see here, that the electron rotate around a nucleus, which is very small and very dense, and these electrons are on quantized orbits. An electron can move from one orbit to another orbit by emitting light with energy equal to the frequency of the light is given by this formula, where the difference is energy is the difference between the energies for the different orbits, and it could recover completely Rydberg's formula. Einstein, 1916, invented theoretically the phenomenon of stimulated emission, and this is very important. It's at the base of laser. And using Planck's law and this also the result from Bohr about energy levels in atoms, he could really understand the different ways for an atom to absorb or emit light, and he discovered this phenomenon of stimulated emission. De Broglie, 1925, had the intuition that if light is both a wave, which we knew from before, and a particle coming from Planck, Einstein, etc., maybe matter is also both waves and particle. And he suggested to introduce the wavelength of a particle as h, the Planck constant, divided by the momentum of a particle. And this was beautifully confirmed experimentally by a famous experiment in 1927 from Davis and Germer. They sent some electrons onto a nickel surface and detected electrons with a pattern in an interference pattern, which is really a signature of wave behavior. Now we come to the famous year, which is the reason why this year now, 2025, is 100 years of quantum, so 1925. Almost at the same time, you have the wave mechanics, which was proposed by Erwin Schrödinger, and with the Schrödinger equation that you see here, and matrix mechanics, which was, I think, discovered by Werner Heisenberg that you see here. And then there is a very famous paper by Heisenberg, Born, and Jordan with the this matrix mechanics. And first, they did not agree with each other, but very rapidly Schrödinger showed that actually the two formulations of quantum mechanics were equivalent. And a little bit later, Born could interpret this wave function that you have in Schrödinger equation with the idea that the square of this wave function represents the probability for a particle to be somewhere at a certain time. Maybe one more thing in this little bit historical description of the beginning of quantum mechanics. Paul Dirac, 1926, formulated a Dirac equation that really include special relativity in the formalism. So now together we have the input from Albert Einstein and in quantum mechanics. So the success of quantum mechanics was very, very fast and very large and really revolutionized physics, physics of the microcosmos, with really a new area, quantum field theory, quantum electrodynamics, strong impact in optics, creating a field of quantum optics, laser, which was discovered in 1960, and completely revolutionized atomic and molecular physics. You have the start of the quantum chemistry, nuclear and particle physics, and of course, condensed matter physics. I have shown many men in this presentation, and I will show many more men, but there were a few women, of course, who contributed to the beginning of quantum mechanics. Unfortunately, because of maybe historical reason, they are not so well known. At least one of them had a really very strong impact in nuclear physics, Maria Gopattmayer, and she is also very important actually in my own field of research. She predicted theoretically the possibility for multi-photon processes already in 1931. So now I'm coming to the second part of this talk. Can we observe the quantum world? The fathers of quantum mechanics had some doubts about their theory. Their theory was very, very abstract, very mathematical. And here is one question from Erwin Schrödinger. Can we perform experiments with individual quantum system? And here is a citation from him. And he said, we never experiment with just one electron or atom or small molecule. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences. And this is from 1952. We have learned to actually do experiment with only one or a few quantum system. And let me show you two examples. The group of David Wineland and also other group, of course, in the world have managed to isolate a single ion in a trap and then do experiment with this single ion, manipulate and observe the states of this ion using using photons, using interaction with laser light. And he got a Nobel Prize a few years ago for this. Here you have a picture showing a trap for an ion, and it's possible to really cool down these ions to extremely low temperature and to control the degree of freedom of the ion by absorbing or emitting photons. Another example of this control of individual quantum system is what Arosh and his group managed to do by isolating and manipulating a single photon or a few photons in a cavity, and observing this photon or the state of the electromagnetic field in this cavity by using atoms in Rydberg states, and again using light matter interaction to manipulate and control the state of the electromagnetic field. And he shared the Nobel Prize with Wineland for this control of individual quantum system. Another question that Einstein raised in 1931, which is very famous, is quantum mechanics complete? Can quantum mechanical description of physical reality be considered complete? And this is actually the title of a very famous article from Einstein, Podolsky, and Rosen in 1935. And here's a citation from Einstein in a letter to Max Born, 1947. I cannot seriously believe in it because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky action at a distance. This is a very famous citation. And what Einstein had a problem with was the prediction from quantum mechanics for entangled pairs of particles, where according to quantum mechanics, if you make a measurement on one of these particles, this affects immediately the state of the other particle, even if they are spatially separated. In 1964, John Bell invented an inequality which allowed for experimental tests of the prediction of what Einstein suggested, called local realism, versus the prediction of quantum mechanics. And a few years later, there were several generations of experiments performed by John Clauser and Friedman, Alain Aspect and co-workers, Anton Zellinger, and many others, that actually showed that the experiments are in agreement with the predictions of quantum mechanics. And Clauser, Aspect, and Zellinger got Nobel Prize 2022 for these experimental discoveries. And here is the idea of this type of experiment. They work with entangled pairs of photons and detect the state of the photons using a correlation type of measurement. And this was very important because it led to really what is now called the second quantum revolution, or it's the birth of a new field called quantum information, with three areas. One is quantum communication, allowing secure communication, quantum sensing and metrology, allowing for ultra-sensitive measurements and diagnostics, and also quantum computers and quantum simulation, allowing to perform optimization calculation very, very efficiently. Finally, another question is, can we observe the quantum world? And here's a citation from Werner Heisenberg directly in 1925. The formal rules which are used in quantum theory for calculating observable quantities may be seriously criticized on the grounds that they contain, as basic element, relationships between quantities that are apparently unobservable in principle. And here we can ask the question, can we measure not only the square of a wave function, but the wave function itself, its phase and amplitude? And can we follow in time a wave function? So now I'm come to the last part of this talk, which is a little bit of attosecond physics. Can we look at electron motion using attosecond pulses? First of all, how do we create attosecond pulses? Attosecond pulses come from a very, very nice quantum mechanical process, which happens when atoms are exposed to strong laser field. And here is a picture of this process. What is represented here is the potential of an atom, and the blue thing is an electron in the ground state, which is in the atomic potential. This potential is strongly deformed by the laser field, so that one wall is going up while the other is going down, so that you have a potential barrier. This implies that the electron in the ground state can then tunnel through the potential barrier. Then the electron is driven away by the laser field. So quantum tunneling is also one of these beautiful quantum phenomena that does not exist in classical mechanics. So the electron, which is now free, is driven away by the laser field, but the laser field changes of sign so that the electron is driven back towards the atom. And then there is a certain probability for the electron to recombine back to the ground state. And in this recombination, you have emission of light in the form of a short, very short light pulse, duration a few hundred of attosecond. Let me stress that this is really a quantum process. You should see that as an interference between the wave function in the ground state and a small part of this wave function that is going away, coming back and interfering back to the ground state. So in the time domain, since this process can be repeated actually twice per laser period, in the time domain, you obtain a train of a series of very short light pulses in the attosecond range, while in the frequency domain, you have a comb of high-order harmonic of the laser light. And this led to Nobel Prize to Pierre Agostini, Ferencross, and myself in 2023. So what can we do with this very short light pulse? Well, we can look at the quantum world. And for example, let's go back to the photoelectric effect, which I introduced at the very beginning. When Einstein looked at this process, he was concentrating on the properties of light, which is both wave and particle. Now let's concentrate on the property of the photoelectron. I'm sure that most of you think of this photoelectron as a particle going away and being detected with a certain energy momentum. But we know that this photoelectron is also a wave. So what are the wave properties of a photoelectron? What is the phase? And a little bit more generally, what is the quantum state of the photoelectron? Let me take an example, a very classical, beautiful quantum phenomena, quantum interference in the photoionization of helium atom close to a doubly excited state, as you see here. So this is a beautiful example of quantum interference. Helium can be ionized either directly by absorbing a photon or via excitation of this state, which then decay by Coulomb interaction. This is called auto-ionization. So here you have two paths going to the same final state, in quantum mechanics, you add amplitudes, you have a quantum superposition of state, a quantum interference. And this process was actually studied in the 30s by Ugo Fano, leading to a very, very, very nice publication, 1961. So usually this phenomena was studied just measuring the intensity of ionization. But now, thanks to our attosecond techniques, we can also determine the phase of the photoelectron. How do we do that? Again, we build a quantum interferometer by using here different harmonics and superposing infrared photons here to make an interferometer. So here we make a copy of this wave packet here, a little bit below in energy, and we measure interference between this path, which is affected by the presence of the discrete state, and the other path here, which is not affected by the resonance. And through this technique, this interferometric technique, we can measure both the amplitude and the phase of the photoionization. And here is a result where you see a very nice interference pattern for the amplitude, and as well as a phase variation, which is here equal to pi. What is very nice, since we have determined the phase and amplitude, then we can go to the time domain by Fourier transform and really look at the wave function of the electron in the time domain. We can even follow the variation of this wave function, both in frequency and time, using the Wigner representation as shown here. And we get this temporal behavior as shown here with first, as a function of time, direct photoionization. This is the yellow part, which is broad in frequency and rather narrow in time. And then you have a strong interference pattern here in the middle when the two paths have comparable amplitude. And finally, at longer time, you only have the process via photo excitation. So we can really follow this photoionization process in the time domain. Finally, we can also measure the quantum state of the photoelectron. In some cases, it's very difficult to characterize a photoelectron as a coherent wave with a phase and amplitude. We need to do something better. We need to do a tomography of a photoelectron. And this we do by using a probe field, which is composed of two different frequencies, so that we can, again, it's an interferometric measurement. We go to a final state via different paths, this path here and the other path, so that the interference pattern that you will see will depend on whether there is a phase relationship between these two regions of the photoelectron. And through this technique, we can measure actually the density matrix of a photoelectron. So it's in the continuum, so it's energy on both axes, and the diagonal is in this direction. This is obtained in argon. And in this case, we see a density matrix, which is oval. So there is a loss of coherence in these two regions, which we could interpret as due to entanglement between ion and electron, in this case, because of the spin orbit splitting of the argon ion. So with this example, I would like to conclude this presentation and thank you for listening. And this is a photograph of my research group in Lund. And let me say again, using the logo of this International Year of Quantum, that quantum science has had a huge success, both in fundamental science and in technology, and it is just the beginning. Thank you very much for your attention.
Thank you very much, Anne, for this very instructive and very clear presentation. So now we'll go for the second part, so with having more reflection and dialogue, so by inviting Professor Ponce and Professor Kasry on the screen, so that we can start the reflection on quantum world.
Thank you. Thank you very much.
With the questions.
Yeah, so sorry, please go ahead, Silvina.
So then, Amal, can you start?
Amal, are you going to start with your questions?
Yes, okay, sure. Thank you very much. Professor L'Huillier, thank you so much for this insightful talk, that it was really very clear and the simple language. And I think everyone, even non-physicists and even non-scientists, can easily understand or at least get an idea about what quantum is. And we are really grateful for this. I want to follow up with a couple of questions. You mentioned also during the presentation, also it was about quantum, you spoke about attosecond, and you are one of the experts in the field. This field is seen as the pinnacle, actually, of fundamental physics. From your experience, what are the necessary conditions, scientific-wise and institutional-wise as well, or also educational? What are these conditions that allow a country or research environment to nurture such advanced research? And how could UNESCO and its partners help foster these conditions in regions where quantum research capacity is still emerging?
I would like to encourage even the small country to do this kind of research, because it's not you don't need the big instruments or big machines. You can do that in a university environment. So you need lasers and vacuum equipment, because this radiation, of course, is absorbed by air. Lasers, when I started 40 years ago, they were quite expensive machine, but there is really a progress in laser technology, and now the lasers that you need to do this kind of research are much both cheaper and user friendly than the one we used before. So they are becoming affordable. So I would say that this type of research is not yeah, it's I think affordable. Yeah.
Okay, thank you very much. I think you already actually answered my second question, which was about like the entry point. How can countries go into this? And you mentioned a couple of things that the research environment can start with. So let me move to another point.
I can add something else.
Please.
In addition, there are now facilities that provide this type of sources, both in Europe. This is called infrastructure in different places in Hungary and in the Czech Republic, and also in the States and in China. Groups from all over the world can apply for beam time to these facilities. So even if you don't have the environment in your own university, you can get help.
Yeah. Thank you very much. You actually answered the two questions perfectly, because this is definitely an entry point that the member states or countries that don't have any facilities, they may start by applying and sharing infrastructure. And this is something at UNESCO we encourage. We have a big program actually, to share infrastructure with the scientists in the global south. So my second question is about actually communication. So at 2 seconds, science is a breaking achievement in fundamental physics, but it still can be considered a bit complex for some students and for the general public also, or even for some scientists if they are not experts in the field. From your experience, what do you think the most effective way to communicate such advanced research? I mean, you gave us a very good example today, but what other things could be done to communicate such what can be considered the complex field of physics?
I can tell you that myself and also my two colleagues that got the Nobel Prize and other colleagues, we are now, thanks to the Nobel Prize, we are really going around and presenting this physics, I think at a very easy level. And myself, I'm presenting this to children in schools, and you can explain a few concepts in an easy way using, waves and analogy with music, this kind of thing. I think in general, if I want to say that more general, I think that it's important that the scientists do this effort to go to the general public and present what they do in a way which is understandable. I think especially now it's important that scientists do that. When you get the Nobel Prize, you have to do it, but and you get the invitation all over the place. But I think this should be generalized to many more people to do this communication effort.
Thank you so much. This is a very important message for all scientists. And now I give the floor to Silvina to ask, to follow up with you on questions.
Thank you, Amal, and thank you, Anne, for the beautiful talk. So I'm going to move to something slightly different, which I've been reading the autobiography that is included in the Nobel Prize website. And I've seen that you describe how you managed to combine family and career. In particular, that you obtained a professorship position in Lund that had been open for women. And so now I would like you to reflect on the role of this type of targeted policy of a positive discrimination. What do you think about them, like targeted professorship positions or awards like the L'Oreate UNESCO award? How they affect the self-esteem of the people who are benefited from that? And what do you think about all of that? What you can tell us? Thank you.
It's a really difficult question, and I for me it's a difficult. It's a little bit a problem because I think in general positive discrimination is not good. I mean, it should be fair for everyone, both men and women and people from all over the world when you have a position or a prize or something. At the same time, I know that I have benefited from this type of you can say chances in my career. So my opinion on that is again, I think in positive discrimination in itself is not really good. However, I think there are so few women in some areas of science and especially physics that it's important to not let the competent women disappear. So measures to help keep them, I think, are important. In general, awareness about this gender gap, I think it's important, and there are many things you can help to keep the woman in science.
Okay.
So that's I don't have a clear answer because I think it's a very, very difficult question, and it's not good if you have quotas for women and men, that I really am against, but to help the women, especially in the field where there are so few, I think is important.
Okay, thank you. So it's necessary to find a good balance of different
Yes.
types of policies. So the other question is about education, that I read that you also enjoyed teaching, and particularly to students not from physics, but physics engineering. And since this is the International Year of Quantum, I would like your reflection on whether you think we should teach that quantum science, particularly quantum mechanics, should be included in the curriculum of various STEM careers beyond physics, and also if it could be included at the secondary school level.
I think it's a difficult question.
Oh my goodness.
Yeah, because I still, of course, I think it's well, you can teach waves and optics to secondary schools, and I think it's important to do that. Quantum mechanics, for me, it's requires a certain degree of mathematics, and if you really want to understand it, I'm not sure anyone can understand it really, but if you want to understand a certain level, you need to have a certain background of certain abstract level, and I have difficulty to see that in school. But however, you can do a lot of very interesting, I would like to say, cool physics in schools that illustrates some very easily some quantum concepts. And I'm thinking, because I like lasers and I like optics, of course, of optics experiments. Yes.
Okay, thank you. I think we can now include some of the questions by the participants. We had at some point over 300 participants. Now we have a little less than that. Anyway, so one of the first questions is, what would be the recommended best reading to develop basic learning on quantum science and also qubit, I guess, quantum information, quantum computation?
I'm not sure I have the best person to answer this question, so I don't know.
Okay. Then another question is, if we study an isolated quantum system, can we be sure that its nature is not altered?
I don't know. I mean, this is too. I need to think a little bit.
Well, I guess
think
it's related to the process of measuring that
exactly.
when you measure, you collapse your system. So
yeah. Yes, but we know how to do that without this non-demolition type of measurement. You can do that. So I can answer in the physics that we do. Of course, we collapse our system, but somehow we do. It's about doing interferometry, and what we get give us tells us what is happening before, so to speak, the collapse. Yes.
Okay, thank you.
So what I mean is, what I want to say is that what we are able to measure using, we are not violating anything from what we know about quantum mechanics. What we have been able to do is achieve such a degree of control of the light, both in the extreme ultraviolet region and in laser light, and under very short pulses, that we can really interrogate matter in a very precise way, and this is how we do this type of measurements allowing us to, for example, understand what is the wave of the phase of a photoelectron. Yes.
Okay, thank you. Let me move to a more social type of question. What made you study physics? How do you keep yourself motivated to do science every day?
I think I have a passion for physics, for doing research in physics, and this is what keeps me motivating every day, is to understand the next step in what we are doing. There are always things which are not clear, and we need to do experiment, we need to interpret. So I would say it's the passion for learning that keeps me motivated every day. What made me study physics was interest in, I would say, mathematics and physics in general, and the understanding of our world. Yes.
Okay, so there is this more technical question. What makes the excitation and relaxation that fast, attosecond fast?
The attosecond timescale is really the timescale of electron motion. So if you take the simple Bohr's atom model, which is of course not the right physical picture, but if you calculate the time for electrons to rotate around the nucleus in the lowest level, it's 150 attosecond. So it gives you the time scale. So when you have a electron transition, it's the time scale for things to happen is really a few tens, hundred of attosecond.
Thank you. Then what do you think is the most promising among the open problems in quantum mechanics or maybe quantum science now?
This is also a very difficult question. I think there are many very exciting things happening at the moment, a little bit in several areas of the quantum physics. Of course, quantum computer is very fascinating, and looking forward that this happens in a way where it really become an advantage compared to a classical computer, at least for some problem. What we are doing, coming back to my own field of research, I think looking at a very, very fundamental light-matter interaction in both for atoms or molecules in this time scale is also very fascinating. And looking at this quantum phenomena like entanglement and decoherence with this available time scale is very fascinating.
Then there is another question also on the technical side. Can you explain how it was possible to capture an image of the photon by probing the quantum electromagnetic field?
Now you are referring to the work by Serge Roche, where they trap photons into cavity, and so these photons were measured by having transition between states, between Rydberg states in I think alkali atoms. So this is how it was done. Fantastic work.
Thank you. Then there is a question from a physics graduate student, I guess from Africa, because he's asking how specifically African students could use this information, the information you gave, to show their community that there is something that could help them in terms of technology. So from quantum science to technology in a region like Africa.
I am not sure. I don't know, but I think you probably can answer this question much better than I can do. Again, I would like to say that there are things that we can do, I'm sure, in Africa, because this type of experiments is not so expensive. But I think there are people that can answer this question better than I do.
Okay. Then there is a question. May I ask if attosecond laser pulses are the ultimate time limit that this technology can achieve, or if shorter laser pulses are possible?
Yes.
Even using nuclear transitions.
Yes. In principle, there is no fundamental limit. It's more technological limit at the moment. The record is 43 attoseconds. This is what we can do. The difficulty is in order to have a very, very short light pulse, you need very, very broad bandwidths where all the frequency components are synchronized. And we know how to make very large bandwidths through this process I mentioned, leading to these high order harmonics. But we don't know yet how to make all of these frequency components be in phase with each other. So, but it is more, again, a little bit technological question more than fundamental one. So I don't think this is a limit. I think there will be shorter pulses in the future.
Then there is another question. What are the general applications of attosecond physics?
Yes, application are, most of them are are still very fundamental. And I would like to say the challenge of attosecond physics is to extend the measurement that we can do from simple atomic systems to more complex matter, like condensed matter or big molecules, and really to use this technique to follow electron motion, electron transition in this big system. And if we can do that, we can probably also control this transition, which are often the beginning of for example, a chemical process.
So finally, I think we can ask one last question, and then if you want to say something else. The last question is, how do you see the impact of artificial intelligence is now on quantum science and technology?
I'm not the best person to answer this type of question. I think, but I can say that I'm convinced that artificial intelligence will have a strong impact in society, and especially, and also in science. Absolutely.
So, dear Anne, I don't know if you want to add anything else, particularly for the international scientific community.
I think I would like to thank you all for listening, and I would say especially to the young people, I would like to encourage them to if they like physics and quantum. I think it's a great area of science, and there is still a lot to discover, especially as the technology progresses. We talked about artificial intelligence, but there are many other areas with strong progress, like in my area, lasers. So I think it's very open. As said in this logo, is just the beginning.
Thank you, Anne. I don't know, Amal, if you want to say some last words.
Thank you very much, Silvina, and thank you, Anna, for all the answers. And maybe I can just quickly jump in here to comment on one of the questions from Africa related to the scientists in Africa. Of course, scientists, Nobel laureates like Anne and others can support greatly on that. I would just like to mention that we have a big program from UNESCO to support the scientists in Africa by sharing sharing the scientific infrastructure, the laboratory equipment remotely. And my colleague Jing will add here in the chat the link to this initiative. Scientists can apply, expressing their needs, what exactly they are looking forward to, and we try to connect them to the available laboratory facilities to be able to connect and share their need. Also, in order to support the scientists, specifically in the field of quantum science and technology, we recently launched a survey. My colleague Jing will also add the link. She added it already, but she will share it again now. And I urge you, please, all of you, to respond to this survey, because it will really help us a lot understand where the gaps are and how we can help in reducing the gaps. One of the main aim or goals of the International Year of Quantum Science and Technology for UNESCO is to identify the gaps and also to try to reduce these gaps by developing programs and activities and also engaging the stakeholders in order to hopefully reduce the gaps between the North and the Global South in this field, because it's very important that there is an equitable share of knowledge and technology. So to end, I'm really happy. It was really a very successful launch of this IUPAP UNESCO curricula that we hope to continue with more excellent talks like today. But as I said, we would also hope that it will not be only talks or lectures, but also a platform really to engage the public and to share more knowledge. And as we move forward under the umbrella of the International Decade of Sciences for Sustainable Development, we hope to share and show how the science can help in achieving SDGs. I thank you very much all. I thank you, Professor Anne L'Huillier, for this insightful and great talk. Thank you, Silvina. Thank you, Christine. Thank you, Jean. And thank you very much for the over 300 participants and audience who listened to us today. And I look forward to seeing you next time. Thank you.
Thank you, and stay tuned for the next colloquia. And I'm sorry that I couldn't ask all the questions that were put in the Q&A, but thank you for your questions.
Thank you. Bye.
Thank you.
Bye-bye.
Bye.
Bye. Bye-bye.